Okay, hi, good afternoon or morning, wherever you are in the world, to the first technical talks for the EAGE Seismic Acquisition community with the topic Deep Sea Mining Exploration, Exploitation and Environment. This session will be recorded, so it probably will be made available afterwards to the community. So please switch off your camera and microphone to spare the bandwidth for those with a poorer connection. I would like to give the word to Rudy Helmons from the TU Delft. He will start with a presentation on deep sea mining and overview of recent developments.
Okay, thank you for the introduction. Yes, so first let me introduce a bit more about myself. I have a master's degree in mechanical engineering, and in 2017 I obtained my PhD in the field of dredging engineering. And effective dredging engineering, in my perspective, is to put it, deep sea mining is a special case of dredging engineering, how I see it. During my PhD, I also worked at Royal IHC, and afterwards I joined TU Delft permanently as a position of assistant professor in the field of offshore and dredging engineering. And since this year, I'm also adjunct associate professor at NTNU in Trondheim, Norway, also for the field of deep sea mining. And most of my research is related to those physical processes that are highly relevant for especially the equipment used for deep sea mining. And in this talk, I will mostly focus on Exadero. So that is about the excavation process for rock and underwater conditions. And I'll slightly touch upon the project of Plume Flock. And I expect that Wiebe Boomsma from IHC will probably focus a bit more on the Blue Housing project. And I assume that Henko, the Stigter from Dutch Sea Research Institute, will also touch upon the GPI Oceans Mining Impact 2 project. So that's, I think, a nice distribution of the activities. So first of all, why would we consider deep sea mining? I think in general, the biggest challenge that we're actually facing is that with current technologies or with developing new technologies, we need materials to actually manufacture the products. Just think about offshore wind, the wind turbines. We need materials to build or to manufacture the permanent magnets. For electric vehicles, think about the battery packs that need to be produced. And if you just take a look at this example of a cell phone, how much valuable materials need to be incorporated to actually make it work. And as we see, especially for the European Union and for the United States, we know that for quite some materials there is a risk whether the supply will be sufficient to accommodate the ongoing economy. Especially for the raw materials, for instance, for the electric car vehicles, we need more materials to actually manufacture them. Because if we take a look at this overview in the top right, so if you follow the entire value chain for where materials can come from, recycling is not always the full option. In any phase of the process, there will be some losses in terms of material that cannot be recovered. So there's some waste. So we need to be able to grow the circle. But another thing, especially for the example of the electric vehicles, you can only think about recycling if they are at the end of their lifetime. We cannot already start recycling the new Teslas nowadays. So we need to grow the circle to make it possible to actually manufacture all the vehicles that are needed. If you then also consider from a more technical point of view, or for the especially for the EU, on the left we see some of the materials that are in high demand for new technologies, and the higher or the more red they are, more critical they are, or the more prone they are to, say, a supply risk. And as you can see, especially for car batteries, offshore wind, for motor photo cells, there is a need for quite some materials, and especially in the examples of, for instance, cobalt. That is a material that is highly abundant in the deep sea deposits. So that's where deep sea mining could provide an option. And one thing to keep in mind when we consider the need for raw materials, on one hand, it is about products and being able to provide the products and technology that are needed. Another thing that is of highly relevance for the EU is also that if we can manufacture the products ourselves, it means that we have also a lot of economic activity in terms of jobs. If we don't have access or secure access to sufficient of these raw materials, it might be that quite a large part of our economy is at risk. I'm not saying that deep sea mining is the final solution, but at least it is something to consider whether it could be a solution or part of a solution. If we then take a look at deep sea mining or the type of deposits that are most relevant, there are three categories that are of most interest. The first category are the so-called hydrothermal vents. They are rich in copper, zinc, gold, and silver. Currently, there are about 7 exploration licenses provided by the International Seabed Authority, which acts on behalf of the United Nations to manage the waters beyond the exclusive economic zones of independent nations. And these hydrothermal vents are typically found at water depths beyond 1 kilometer water depth, and they are most profound or most conveniently found along the ridges of the tectonic plates. The second example are polymetallic nodules. They are mainly of interest because of the high content of cobalt, nickel, and copper. Often they are also referred to as manganese nodules because manganese is the material that is most profound in them. But the economic interest is not for the manganese, but more for cobalt and nickel. This is also the type of nodule or the type of deposit that has gained the largest economic interest at this stage. And they are typically found in 4 to 6 kilometers water depth at the abyssal plains. And to give an idea, these nodules, like here on the left, they are typically in shape and size comparable to potatoes. And they are abundantly distributed on the seafloor, just to be picked up. They lie on top of the seabed in quite a muddy seabed. And finally, we also have the ferromanganese crusts. They are most interesting because of the amount of cobalt and rare earth elements. And these are, in terms of composition, quite comparable to nodules, but the main difference is that they are not distributed on the seabed in nodule shapes, but more it's deposited along seamounts. In typical layers of a few centimeters to 40 centimeters thickness. And these are typically found at 400 meters water depth to several kilometers. The main reason, or one of the main reasons in this stage for deep sea mining to consider, is that there are quite a number of the so-called battery minerals. So that's here on the right, you can see an overview of, say, typical material or mineral composition of the polymetallic nodule. So you can see that manganese is abundant, but also very high grades of nickel, copper, and cobalt. If you then consider deep sea mining, or say the license areas that are currently granted, and how it compares to the scale of how the area or the international waters are managed, I think that this picture will gives a very nice overview. In yellow are those areas that are granted as exploration licenses by the International Seabed Authority. At this stage, the rules and regulations for exploitation licenses are still under development, and they are expected to be delivered, or at least to be finalized in 2023. And in the International Seabed Authority, the rules and regulations have to be adopted by consensus of all member states that have ratified the United Nations Convention on the Law of the Sea. So not all countries have signed the UNCLOS. If you look here at this graph or this diagram, yellow are the areas that are the exploration licenses that are granted. So we have in the middle of the Pacific, the largest area that is in the Clarion-Clipperton zone, mostly for nodules. But here in the Atlantic, there we have seafloor massive sulfides, so the hydrothermal vents. And in the Indian Ocean, there are nodule areas, as well as hydrothermal vents and crusts. So just to give an idea how a generic deep sea mining system looks like, we start at the bottom because you need to excavate the material somehow. So we have a seafloor collector. This can be for nodules, a collector system that just picks up, but it could also be for vents and for crusts that is equipment that will actually really excavate material. The ore that will be collected will be transported to a vertical transport system, through most likely through a slurry lift. It will be transported to the vessel. At the top, at the vessel, the ore will be dewatered. The excess of water and all the sediments that are in it that are not of economic value will be deposited back to the seafloor, or at least back to the water. At what water depth, that still needs to be, that's still on a debate, whether it's below a certain water depth, or whether it has to be returned to the deep sea back to the seabed. In terms of, or this one of the items that has a lot of attention in terms of environmental impact are the so-called turbidity flows, or the plumes. The most profound ones are those collected by or generated by the return flow. So that's what's here depicted in the middle, and also by the excavation process. So when you have a nodule collector, it picks up nodules, but it unfortunately also picks up sediment, and that excess of sediment needs to be discharged, preferably as close as possible to the original location. So that's one of the challenges. So now I'll focus a bit more on the excavation process for rock. If we just take a look at how rock cutting, or the rock cutting process actually looks like, on the left we have an example there for a small cutting thickness, and there it means that if you have cut a very shallow depth, we create an indentation, and it more or less looks like a plastic flow. And you can mimic that, or you can envisage it like it's scratching. We also have it on the right. There are exact same conditions to apply. The only thing that differs is a larger cutting depth. And in that case, we actually have indentation, but we also get shear and tensile cracks that occur. And from a technical point of view, the occurrence of those cracks are very beneficial, because that means that we have to provide less energy to excavate a similar amount of material. And as you can imagine, that makes a lot of difference in terms of the design of the equipment, but also in the power consumption. So to take a look at how its process is more dominated, when the tool is being pushed into the rock, it creates a crushed zone. And that's just by indentation. And as long as the overburden is strong enough, that crushed zone will grow while the tool is penetrating deeper and deeper into the rock. Eventually, that crushed zone, or the stresses in that crushed zone, cannot be contained anymore by the overburden, and then it will move towards shear cracks and tensile cracks, and especially those tensile cracks. Those are most of interest for the excavation process. One thing that has to be kept in mind is especially that in underwater conditions, that the cutting force can be dependent on the cutting velocity that is being applied. And that is somewhat shown in this graph. The reason that the water or that the process is velocity dependent is due to what we call dilation. And what you see in this graph is, I'll first start in the dry conditions. That's the line at the bottom. When we increase the strain rate at which we, or the velocity at which we cut through rock, we already see that the strength of the rock slightly increases just for higher velocities. The main reason for that is that the cracks, the micro cracks that are being generated, don't have the time to grow together to really join to large macro cracks. When we do it in underwater conditions, we have this slope move to the top, stating dilatancy hardening, and that effect is when we create a crack, water has to flow in for a crack to open. Water has to flow in, and as the rock is consists of very low permeable material, you can imagine that the inflow of water is restricted by the surrounding, or by the rock itself. So the deeper we go, or in deeper water we can go, the larger the pressure drop can actually go. So what you see in shallow water, the maximum pressure drop that we can get, for instance, in just in ambient conditions, we can only have a pressure drop of 1 bar. But if we go to deep sea, we might even run into a pressure drop of 200 bars or beyond. For instance, in the case of 2 kilometers. So that is what you also see here in the upper limit. So based on the water depth, there will be a limit to what extent this dilatancy hardening effect can occur. Yes. So what we then see is, especially for deep sea applications, that for the excavation process, the crush zone would become larger, and as an effect, the cracks that will occur are occurring at a later stage, resulting effectively in a smaller chip size. Effectively, this means that we need to create more chips. We need to create more fractures, more failure areas or demolish the rock to a greater detail, meaning that we have to spend more energy to do the excavation process. And especially what's shown here is that the deeper water we get, the more resistance we will notice from the water or the ambient pressure to alter the cutting process. And to give an idea how it looks like, here's some results from simulations of our rock cutting model. What you see here on the left and on the right are atmospheric conditions on the left and on the right in deep sea conditions. The colors that you see, blue means that it's fully intact, and the more red it gets, the more disintegrated the rock actually gets. And what's most profound, clearly, on the left, you see cracks occurring and we get larger chips, while on the right, basically, the rock is forced to disintegrate almost entirely. These are simulations based on the so-called discrete element method, which is a method that is very conveniently to replicate rock behavior, but also when the rock fails, that it can actually continue to behave like granular material. So that's very convenient in this case. And that is extended with pore pressure diffusion effects to mimic the effect of shallow water and deep sea conditions. These results are also compared with experiments, and these experiments were provided by IHC. They conducted tests at ephemeral because that's where they had a facility that is able to create or have a pressure tank that is large enough for a proper rock cutting experiment to be conducted. So for these experiments, the range of ambient pressures that were tested varies from 1 bar, so just shallow water conditions, until 180 bar, yeah, comparable to 1.8 kilometer water depth. They also varied the cutting velocity, ranging from 2 centimeters per second up to 2 meters per second. And although this was focused for research on SMS, it was selected to use a limestone. The main reason to do so is that we have to deal with a very tough situation. Either it will be very difficult and challenging to get appropriate samples to conduct the rock cutting experiments. So we might be able to collect SMS, but then we have to cement it in a matrix in which you can then conduct rock cutting experiments. But then there's a lot of disturbances in your experiments because of the matrix and discontinuities in all the specimens that you combine together. The other option, like in this case, would be to select a comparable material, but then have it more or better manufactured. So, like in this case, limestone from a quarry, so which was of a very good quality, so that you really can investigate the rock cutting process itself and don't have to worry too much about all kinds of discontinuities and uncertainties in your analysis. Because as you can see in the setup, you place the rock or the specimen inside the tank, you conduct the experiment, and then you can only see what the outcome. You cannot see what happens during the experiment. So that's quite a challenge. What we see here are just a few examples. I've shown the most extreme cases. So for A, so on the that is a low velocity in ambient conditions. For B, that would be low velocity in hyperbaric conditions, so in deep sea. For C, that would be high velocity in ambient conditions, and D, that would be high velocity in deep sea conditions. And what is most clearly shown, especially on the bottom right, there we have laser scans of the grooves that are generated by a single tooth. And there you can see in black all the different profiles, and in red the average profile of that block. And what's most profound here is that for low velocity and low ambient pressure, the production would be highest. And for the case of D, high velocity, high pressure, the cutout profile would be most closely to the shape of the chisel itself, meaning that with a single groove, we produce less rock. Then on the left, we can also see the cutting forces, that for the larger the hyperbaric pressure gets, so the ambient conditions or the water pressure, the higher the cutting force in general. So those are two mechanisms, larger forces and lower production, resulting in significantly larger energy demand to do the operation. To give an idea how it looks like, we have the red dots are the simulations, and the gray line is the experiments that we've just shown, but then at low velocity, and the brown line is the same experiments, but then at a high velocity. And on the x-axis, we see the hydrostatic pressure, and on the y-axis, the horizontal cutting force. So the force needed to move the tool forward. And what we see for these types of rock, close to the point where the hydrostatic pressure is comparable to the tensile strength of the rock, that the behavior starts to deviate. And that means that in the case of of water depths below the tensile strength, the tensile failure in the rock is dominant. Well, when we go to deeper waters, actually the process starts to become more and more dominated by the shear failures. And as you can see here, also the effective cutting force increases with the increasing of the cutting velocity. Then we have,
Rudy, I'm sorry to interrupt you. How many more slides do you have? Because we're running over time with the presentation.
a few more. I'll just
yeah, if you can round it up quickly, then please, because otherwise we will run over time a little bit more. Thank you.
Okay. Then I'll just cut it short. We're also involved in new research related to what we call plume floc, which is about minimizing the plume dispersion through natural flocculation. That's also a project together with NIOZ. And in the laboratory, we recreated a log exchange experiment in which we test how the turbidity or how the mud would behave in terms of outflow. So here on the top, we have for artificial sediment that that mimics the properties of the seabed, deep sea conditions. At the top, it's a clay, just a pure illite. At the middle, it is in fresh water, and at the bottom, it is in salt water. Just to give an idea how it looks like for initial concentration of 10 grams per liter. But if we would be able to work with higher concentrations, so that's also for the collector plume, if we would be able to increase the concentration, we get something different. So now the conditions are identical, except the initial concentration, showing significantly different behavior in terms of where the plume would actually travel. So yeah, just to wrap up, we have the plume floc project, which is part together with NIOZ and funded by NWO, and the rock cutting experiments and simulations are part of two projects, Exodero and Exodero 3D. So that's about it. Thank you for your attention.
Thanks a lot, Rudy, for your nice presentation. I hope everything was clear. Is there anyone who has a question? So Rudy won't be there after the session to ask any questions. So if you want to ask one now, and otherwise we will move on with the next presenter of today. So that will be Adriana. Thank you, Rudy.
Thank you.
Shall I start? Can you hear me?
Yes, sorry. Yes, we can hear you. Please.
Okay. Okay, yes. So hi, my name is Adriana Citlali Ramirez, and I will talk about exploration technology for deep sea mining. I will start with a little bit of our motivation, and then I will go through the high resolution 3D seismic case and our study that we did last year, and then the Moon Ridge collaboration in 2022. So the world is mining, the world needs at least 1.7 trillion in mining investment in the next 15 years to help supply metals that are needed for the energy transition. And if we look at the current state of mining and the current amount of minerals that we have and metals that we have, we need to really increase the mining everywhere. And there's advantages and disadvantages to mining onshore versus offshore. But right now, for the energy transition, what we see is that there might be more advantages to mining offshore. So we start with the fact that metals need metals. And mining for particular metals, as Rudy has explained in his talk, that are needed for the energy transition, they are highly geographically concentrated in the world. So for example, between China and the Democratic Republic of Congo, they produce around 70% of the cobalt of the world and 60% of rare earth elements. That's numbers from last year. So one of the challenges that we have with onshore mining is that most of the production is driven by fossil fuel. There is very intensive in terms of massive production equipment, is very intensive also in terms of transport, and all of it has a very big carbon footprint. In addition, there's a risk of pollution, not only of air and soil, but also a lot of aquifer. And quite often, there's nearby where people are living. There, even in several places where mining, this highly concentrated mining exists, there's child labor and lack of safety regulations in other industries. On top of that, the ore grades have been declining steadily over the years, and nowadays the average ore grade is around 1%. So that means that to extract the same amount of metals and minerals, you need to use more energy, and it costs you more and more. Now, on the deep sea mining side, deep sea actually requires, in principle, and this is still on their, it's not all set in stone. There's a lot of activity and research and development in this area, but it seems to require less equipment, less massive equipment. It can be used, you can use decarbonized fuels, and it has a lower CO2 footprint. The ores are higher grade, especially for cobalt, copper, and nickel. So again, you can extract more. It depends again on the type of sulfide or deposit that you're looking for, but it can be a lower footprint. On the other hand, there is still a pollution risk, and there is a debate on how big of a footprint is the environmental footprint of deep sea mining. So just to emphasize the need for more minerals in the energy transition, if we look at this picture from the IEA, an electric car needs around 6 times more minerals than the ones used for a conventional car. And as we're moving more and more into electric cars, this is a huge demand. All energy transition actually requires minerals, and offshore wind is around 9 times more than natural gas and fossil fuels. So it is a huge demand. The fact that all of this is connected through electric networks means that copper is one of the highest in demand. Just between now and 2040, it is expected that the grid lines are going to be doubled. So it is a huge demand. In some of these minerals is more than 30 times demand in the next 40 years between what we have now and what we should have in the future. So all of it is motivating the research and development of technology on deep sea mining. Now, there's different options in deep sea mining, and Rudy actually mentioned the 3 different ones, which is vents, hydrothermal vents, nodules, and crusts. The ones that are a little bit more compact and have a minimal footprint and the highest grade would be the hydrothermal vents. And this is what I'm illustrating here is an active one, which is also known as a black smoker. So these smokers are like geysers. They're like the geysers that you have onshore. But what happens is that they are within the spreading ridges in the deep waters. So in these ridges, you have magma that is trying to go up. The ridges are spreading little by little. And then there's fractures that occur in the crust. So the magma goes up and creates new crust, but it also is fractured with this movement. So through the fractures, there's water that is infiltrated, and this water becomes very hot, very warm by the magma. And when it is warm, it has a reaction with the rocks here. And then because it's less dense than the rocks that are surrounding it, it wants to go up. So it actually goes up as a black smoker. And then the water over here, because we're talking about a bathymetry of, in average, 2,300 meters. So this is very cold water, and it's going to cool it down very, very fast, and it's going to dissolve and make these sulfide deposits, which are like, it will have some sort of nodules with the different type of metals. And then after a while, this is going to become inactive, and it's going to be soon be covered by a layer of pelagic mud. And that layer can be just a few meters or hundreds of meters, but it's not very thick. These sulfide deposits are not that big, so they can range from something around 100 to 300 meters in extent horizontal, and just a few decameters vertical. So they are expected in different parts of the world, but in the Norwegian area, for example, this is the border of Norway. There's a lot of them have been located already in this area. So Norway actually is a country that has passed a law to license for production, exploration, and exploitation of minerals in the Mons Risk area, is where it is expected to start. And it is expected to start the first licensing round in 2024. So between now and 2024, there's time to prepare and to prepare with research and in terms of what technology is going to be used and how it's going to be exploited. But everything has to be a non-for-profit preparation. So with that motivation, we decided to look into what technologies have been tested already and what technologies could be needed to make a good, feasible, cost-effective exploration in this part of the world. And if we think about it, this is Arctic. So we need to think about the fact that in the winter, the ice comes in. There's also in the spring, there's icebergs. So the season to go there with equipment is very short and is expensive. Now, there has been several hydrothermal vents found in the Mons Risk area. So the Mons Risk area in this case is around 16 square kilometers, and I'm just showing it here. And there is one inactive hydrothermal vent that has been found. The light magenta are confirmed active vents, and the dark magenta are the ones that have been identified, but they are not confirmed active or inactive. The reason we're looking for the inactive ones is because the active ones change the temperature, the local temperature in where these smokers are active, and that also creates certain amount of life. So for environmental purposes, we're not going to be exploiting those. We're going to be exploiting the ones that are not active. So they are expected much more than the amount that have been found. So in this area, it's only around 6 that have been found. So now we need to make some assumptions in order to figure out how many of them we could find. And we made these assumptions that are written here. So we are assuming that the spreading rate is around 15 millimeters per year. We know that there's 6 SMSs already found in the Mons Risk area. And we're going to make first a very big assumption, assume that there's an average of 6 SMSs per 1,000 years. So that means that in 16 square kilometers, there's to be found 6,000 SMS that were created in the last million years. So what technology do we need to find them, given that they are very small, 100 to 300 meters in extent, horizontal extent? So let's make our life very easy and assume that they are 300 by 300, like the largest one. So we're assuming that there's a lot of them, 6 every 1,000 years, and they are covering 1,000 square meters. So the technology that has been used so far is mostly 2D technology. So we started by looking, okay, if we go there with a regular grid of 3 by 3 kilometers with 2D lines of seismic, how many will we find? And we will pretty much just detect around 15% of these 6,000. And that's already a densely sample type of acquisition. On the other hand, if we go with the 3D technology, seismic technology, as the one that we use in oil and gas, then we can literally just map this whole area at once and detect all of them. And this technology will cost us the same as increasing from the 3 by 3 2D lines to 2 by 2 kilometers, and that will only allow us to detect 20%. So with the same price, we will be able to do all of them if we go with a 3D seismic. So that was one of the main things that we were looking at. What is the most cost-effective technology that we can bring to actually identify them fast and try to understand better which ones are active, which ones are inactive, and of course, find how much ores we find in each one of them. So yeah, as I said, there has been several different technology tested. And one of them that has been also considered is UAV multi-beam type of technology. It does have a coverage. In this case, it's much smaller coverage, around 300 meters. But one of the disadvantages of multi-beam is that it doesn't have penetration. So if you have a sulfide complex that is already covered by pelagic mud, it's going to be hard to identify. Also, if you use multi-beam further, like from the surface, what we saw is that the active ones are not going to be that easy to identify, and you also want to know where they are. And they're not easy to identify because as they are active, they change the temperature and they change also the density of the local area, and that will change the multi-beam signatures, so you will not be able to see them, and that's already known from data that has been acquired and is publicly available in the Mariano dataset. On the other hand, a high resolution 3D seismic can cover around 1 kilometer in extent, so you get an aerial cover at each pass, and you can detect deposits that are already buried, which is a good advantage. So it gives you efficiency, cost effectiveness, and you can detect all of the ones that you are looking to detect. Now, is seismic a good tool for it? So we needed to know that seismic was going to have a good signal. And if you look into the sulfides, these deposits, again, the crust is opening, so you have altered basalt, and then you have the deposits on top of them. And if you only look at velocities, there is a range that is going to be invisible in terms of these deposits. However, when you look at acoustic impedance, which is what the seismic is going to be reacting at, the density is what saves the day here, because the density has a definite change. It means that the sulfur deposits on top of the outer basalt are going to be detectable by 3D seismic. So that was quite encouraging. Yes, so last year we tried to get a cruise, a scientific cruise, non-for-profit, to go all the way to the Mons Ridge. We had an environmental permit and partners, but we were not able to do so. And instead we decided to test an analog, which we found in the area of Atlantic margins, where we were acquiring a 3D acquisition for oil and gas purposes. So we repeated one line that we acquired for that production survey with another technology that we wanted to test in the Mons Ridge. And we identified that in this area, is nearby the EGA slide, there are some anomalies, very shallow anomalies that can work very well as analogs for this DSM. So this is the two technologies that were tested. In the production survey, we had a towed streamer acquisition with 12 streamers and 6 sources, no, 12, sorry, streamers at 12 meters depth and 6 meters sources. And the sources is the interesting part. So we had 5 sources, and we shot them in this pattern. It's like an overlap sources, a pentasource, where we shot source 1, then 4, then 2, then 5, 3, etc. And we had every 7.5 meters, we were shooting one source, 50 meter separation in the cross line. So this is the production data that we have for oil and gas. But what we wanted to test was a much more high resolution acquisition, so which is the one that we would like to use in the Mons Ridge. So for the minerals, we tested this technology, which is based on seismic apparition encoding. Each one of the streams, which are ergon arrays that we have for each one of the 5 sources that we were using in the production data set, we divided it into a front section and a back section. Each one of them are having the same volumes. And then we shot them with different ethers, but almost simultaneously. So encoding them with different ethers and apparition encoding, then we were able to shoot these 10 sources almost simultaneously, and then move 16 meters more or less, and then shoot these 10 sources, and then move 16 meters and shoot another 10 sources. That means that these high resolution data had, in average, more than 5 times the amount of sources that the production data set. In addition, we measured this data at 1 millisecond, while the production data was at 2 milliseconds, and it was deblended at 3 milliseconds, while this one was deblended kept all the way at 1 millisecond. So yeah, I don't need to explain the rest there, but let's move forward. So this is the basic workflow what I'm going to show. So our initial results. So we have a deca source data set, and that's with sources at 50 by 8 meters. Then we did, together with Operation Geoservices, a decoding, the signature, and the ghosting at the same time, and then a PSTM with 4 meters output. So if you look into this small section, this is the comparison between the production dataset for oil and gas with a pentasource and the deca source in the bottom. In terms of frequency, so the deca source, we have Nyquist at 500 hertz, and we have very useful frequencies without doing any Q or any compensation up to 230 hertz. While in the pentasource, we had good frequency content pretty much until Nyquist, which is 166.6. So there was a difference, and this is just very raw without doing making any effort to enhance the frequency spectrum of data. Some of the geological observations to demonstrate for us that this was the right technology for the purpose that we were looking at using. So here I'm showing just this is the seabed, and you're looking at just a very small section over here. And what we were looking at is how big can we identify what kind of degrees and how big objects can we identify with a good degree of confidence. So we have geologists looking into this, and what they said is something between 15 and 20 meters, and easily 55 degrees are easily identifiable in this area. And it's similar to what we can identify further deep in this data set. So we had only one sail line, but we migrated it, and that gave us a coverage of 880 meters in the crossland direction because we had so many sources and so many streamers. So I'm going to just show you some depth slices here at the first few milliseconds just below the seabed, and you can see here how the seabed is showing in this time sample. And as we go deep, what we were looking for was objects that we could find as analogs for the DSM, for deep sea minerals. And then you can see, for example, this object is around 300 meters and is of the right shape that we were looking at. And this object is around 200 meters. So we see that even though we were so limited with a single sail line, we are able to identify objects like the ones that we were looking at. And this is the area where we were looking at them. So the next thing that we decided to consider in terms of how are we going to make this even more cost effective when we go to the Arctic is the fact that we don't really need a 50% overlap of sail lines, because we are only interested in the first few hundreds of meters. And after that, in the Arctic, we will have for heat basement, and there's nothing more to image. So we are looking into that. But what we did is we actually did a little bit of work with interpolation of the data to try to extend this a little bit more towards the edge and see how it compares to having 50% overlap with other sail lines. So this is the result of that work. So these are time slices, and these are time slices of the pentasource with 3 sail lines. So this is 1 sail line versus 3 sail lines. And two things that we can observe is, of course, the resolution is completely different. And the other thing is that all the objects that we see in the pentasource are visible in the deca source, with some exceptions of some of the deeps that we will need from the other sources or the other sail lines, which we will have in any case. And for completeness, I can show you that in vertical slices. So this is the deca source This is a single saline of the Deca source. I'm showing slices, vertical slices at these locations. And then compare with 3 salines. So we can see how we are able to extend things all the way to the edge, but we do need the other salines to complement. But we don't, the main thing is we don't need 50% overlap, which is a good thing. But this is going to be tested in any case in our next cruise. So we wanted to also make have an understanding of how much money there is to be made for this to be a good business, a profitable business. So we made some assumptions. These are prices based on last year's prices. And we are assuming that these deposits in the Maastricht, and this is based on actual information from the sites that have been found, and there's already a couple of drills there. So we expect to have 8% copper, 3% zinc, 1% cobalt. There's other metals as well, but we're not using them in the calculation. We're just using these 3 ones. So now, instead of thinking as before that there's 6 hydrothermal events every 1,000 years, we're going to make a more conservative approach and saying there's 2 of them only. So there's 2,000 over 1,000,000 years in the 16 square kilometers of the Moon-rich area, which is just the little part here. So if that is the case, and again, we're assuming that you have 300 by 300 as an average of the hydrothermal event, then I'm assuming this production, water content 40%, mud content 20%, and mining completion 80%. Then we make a napkin type of calculation, and we end up with a value proposition of $62 billion US. So there is a very good value proposition, and there is a need, again, as we have explained, for the energy transition for all these metals and rare earth elements. So what we're doing next year is we're going to do another scientific cruise, but with this time we want to go all the way to the Maastricht. So this is one of the possibilities, depending on where we're looking for a vessel of opportunity, meaning a vessel that is doing some activity in this part of the world for another purpose, so that we don't have to mobilize that vessel from very far away and pay for that. And once that we locate where it is, we would like to try to make a 2D acquisition while we are mobilizing the vessel to the Maastricht area. So if it's in this area, it's going to be a different path, of course. And that is for other types of purposes. Again, this is a scientific cruise, it's a non-for-profit. So we're looking at just doing an imaging for crustal studies and other types of studies in this part, and then acquire a very small area, 50 by 3 square kilometers, no, 3 kilometers in the Maastricht. If we have more funding, we will acquire more, and then do a little bit more testing. So what if we do this, depending on the funding, we are going to do more than we did last time. So these are the 3 different types of deposits. Today I've been talking much more about this, but Rudy actually presented crusts and nodules. And we were looking into the amount of copper that are in these 3 options. And one thing that we see is in a very small exploitation area, you can get the biggest value proposition for copper. And copper is actually the most carbon intensive metal that is in the mining industry. And as I said before, we expect the networks, the electricity networks, to expand to double at least over the next 20 years. So it's one of the most important metals to be found, as well as cobalt. Now, crusts, in order to extract lower amounts of metal, you actually have a larger footprint. And if you're looking for nodules, because they are on the seabed and you have to kind of mine them, you are destroying a much larger or affecting a much larger territory. So in terms of an environmentalist impact and amount of ores that you can find, it seems to be a better proposition than sulfide deposits. But I mean, all of them are being investigated. This is just what we're looking at. Yeah, I already said this. There's different technologies that have been tested already. The 3D seismic, as we said, we expect this to be a good exploration technology to find them, to locate all of these deposits. And it has been tested in analogs as we have done, but there's still things to be tested, and it would be great to be able to test it in the actual place. And the same with other technology like P-cable, which is ultra high resolution, seismic, even more high resolution than what we're proposing, but has a lower footprint. So you will need to, it becomes more expensive for a larger area, but it can be good for field development and other purposes. The same with deep tow EM, DAS, VSPs, etc. So what we are proposing for our MONS 22 is to have a combination of high resolution 3D acquisition seismic as an exploration tool to locate as many of these deposits as we can at once with a lower cost and lower footprint. Once that they are located, and it's pretty fast to process this data, we would be able to pass with an ROV footage because you want to make sure that the sulfide deposits that you identified, that you know if they are extinct or not extinct, if they're active or inactive. Because again, the ones that are good for exploitation, that will be open for exploitation, are going to be the inactive ones. And then once of those are identified, the next step would be field development to really understand and characterize how you're going to develop or exploit that field. And for that, we are proposing, and again, this is more of a test, it's a scientific cruise. We would like to test P-cable 3D and deep EM. Deep tow EM. So these two, we are looking at testing them together with the same vessel to make it more cost effective. And then after that, you might want to test other technologies in any case, because we want to figure out again what would be the best combination for the future. So we would consider, I mean, this is in level of priority. Then we will consider to testing other technologies like multi-beam. And finally, with one of our partners, Halliburton, we will be looking at testing also the drilling technology and having VSP measurements installed for permanent type measurements with the DAS VSP. So yeah, that's pretty much what we are looking to do. It is a joint venture between TGS, MPD, which is the Norwegian Petroleum Directorate, EMGS, Halliburton, the University of Tromsø, NTNU Lab, and University of Bergen. And we are currently looking for more sponsors to work with us. So with that, I would like to say thank you. And if you have any questions, I don't know if the questions are now or at the end of the session, just let me know.
Okay, thank you very much, Adriana. I see Henko is raising his hand.
Yeah, that's right. Can you hear me?
Yes.
Yes, we can.
Yeah, thank you, Adriana, for the nice presentation. I think it's a pity you got no permission to apply this technique really on the mid-ocean ridge there. But you said it was
we got permission to do it. I mean, we had a permit from we're partners since 2 years. Well, last year's acquisition, we were partners already with Tromsø, University of Tromsø, University of Bergen, and MPD. So we did this together, but we didn't get enough funding. And even though the prices, the cost is really is just pure cost. There's no profit at all because no one is allowed to make any profit. But last year we were not able to get the funding to test it at the Mons Ridge, but we decided to use our own money and test it in an analog. But next year we're planning to go all the way.
Yeah, and the analog, that was completely a sedimentary sequence, I understand. At least there was a siliceous ooze diapir.
Yes.
But it was all sedimentary rock.
Yes. Yeah, we did look into the contrast, and the contrast in terms of acoustic impedance is around 20 to 30%, which is similar for some of these anomalies that I showed that look that have the shape that we're looking for and the size that we're looking for in the Mons Ridge. They have the same type of contrast with the sediments around it as the ones that we expect in the Mons Ridge, but of course it's a very different velocity regime. So that's what we want to test it in the real, in the real deal.
Okay, thank you. Looking forward to that.
Thank you, Adriana. We're running over time, so I would like to ask if there are further questions, please ask them after the session. I would like to continue with Wiebe Boomsma on exploitation technology of the deep sea mining.
Yes, well, thank you very much. Thank you very much for the opportunity to present. I hope that my screen is visible and that everybody can hear me. I will give my presentation on the exploitation technology for deep sea mining, and with the subtitle, The Road to Industrial Viability. As you all know, deep sea mining is not an existing industry yet. So the industrial viability is yet to be proven, and I would like to sketch the roadmap towards the industrial viability. I'm trying to go to my next slide. Yes, there it is. I work for a company called Royal IHC. Royal IHC is a equipment and shipbuilding company in the Netherlands. And has been building ships since 1642, although under a different company name back in those days. But I would like to stretch that IHC is a equipment supplier and a vessel builder. We are not planning on doing a deep sea mining operation ourselves. We see our role in creating and building the equipment necessary for mining the deep sea. And why do we do that? Well, as I've mentioned, we are an equipment supplier, but we do like to look ahead. So we like to look into the future of the maritime industry and the future of humanity as well. And there we do see the need for materials and a large quantity of those materials, has already been presented by Rudy. And one of the places where you can find them is the deep sea. So if we look at the roadmap we have for the future in the maritime industry, deep sea mining is definitely a part of that. We do that, like I said, as a equipment supplier. We are based in the Netherlands. In the Netherlands, we build all of our equipment and our vessels. Well, we see this as a global challenge, the shortage of materials, and we would like to be a part of the solution. Rudy mentioned that he sees the deep sea mining as a more or less as a dredging operation, and I partly agree with that, but not to the full extent. IHC has 4 brands: dredging, offshore energy, mining, and defense. And we see the deep sea mining as a deep sea mining operation, so not so much dredging, where you need to combine the knowledge of underground mining with the knowledge of the offshore oil and gas industry and the associated water depths, which is very custom in that industry. When I talk about mining, we mean I'm talking about underwater mining. So this is an overview of the product portfolio of IHC mining. And as you can see, we actually only do underwater mining. So we use equipment very much related to the dredging industry. And we use that to mine underwater in either natural or man-made lakes, tailings ponds, or at sea in shallow water depths. And we are currently working our way towards the larger water depths for deep sea mining. We not only look at the mining process, but also the mineral processing. So separating the valuables from the non-valuable materials. And we like to do that in the most sustainable way possible. In a normal dredge mining operation, it's already quite an environmental friendly way of mining. So you have a man-made lake, and that man-made lake is actually moving through the countryside. Most of the vegetation is removed from one side and planted back on the other side of the lake to minimize the amount of environmental damage of such an operation. So mining and environmental friendly operation can definitely be a match, and we also like to do that for deep sea mining. So in our way, deep sea mining will only be possible if you do it in the most environmental friendly way possible. And if you look at the Sustainable Development Goals by the United Nations, we have many goals, and of course, environmental impact is one of them. But also the other ones, like no poverty, is an important goal. Well, for that goal of poverty, you also need materials. So it is a balance between what is needed for mankind and what is allowable for the environmental impact. So a deep sea mining operation. A deep sea mining operation is a very much an integrated an integrated operation. So you have a vehicle driving on the seafloor, doing its excavation process, and then you have a vertical transport system starting at the jumper assembly, and a more rigid riser system towards the mining vessel, which will be floating in the ocean. And then you have to have the logistics as well, where you transport the material from the mining vessel to shore when it can be further processed. The material will be pumped upwards in the riser section, but of course the water and some remaining materials needs to be pumped back to the water column, and therefore you also need the return pipe, which is shown in blue in this picture. It's not only a integrated piece of equipment. If you look at the technology, it's also highly integrated with the rules and regulations, for example, the allowable environmental impact, and well, all of the social factors which also play a role in this industry. So it is an industry which is looked at from many angles, and therefore we need to make sure that all of the aspects, not only the technical ones, but also the social ones, are looked into in a proper manner. I will now go into the technology needed for exploration, but I would like to start with the technology readiness levels. And that is a system which has been incorporated into our technology development for, I think, over 10 years now, where we try to look at the technology readiness levels and work our way through them one level at a time. So I'm not sure if this system is familiar to you, but at TRL 9 you have an actual system which is proven in an operational environment. And at TRL 1 you only have the basic principles observed. So you try to work your way through to the technology and the validation of the technology one step at a time to end up with a proven system which actually works in practice. And we try to do that every step of the way. So starting with excavation, we distinguish two types of materials which need to be excavated. It's either a relatively hard rock material like seafloor massive sulfides, or it's more a alluvial type of deposit, such as nodules, where you have potato shaped and sized nodules laying on the seafloor, which need to be picked up, which is a completely different process. So the hyperbaric excavation, so the hard rock excavation, has already been introduced by Rudy. This study has been initiated by IHC, I think 12 years ago, where we first looked at the simulations of the hyperbaric excavation. And after those simulations has been concluded, we went to the laboratory in France, where we did many validation tests to be able to validate our simulation results. Also already introduced by Rudy. And then this one, so the results, including the validation results, we translated that into a simulation tool. So this is a in-house developed simulation tool where we can design a excavation, a drum cutter, for example, or a normal crown cutter. And we can determine not by a single chisel going through the rock, but a complete assembly of chisels in a drum cutter excavating all at the same time to see what the reaction processes are, so the reaction forces are, what kind of power you need to drive the drum cutter, what kind of power you need to force the drum cutter in the or in the horizontal motion, so driving on the seafloor, what the reaction forces will be, but also what the remaining seafloor will look like. So you might start with a very uneven seafloor distribution, and after the excavation process, you can actually see what kind of surface you leave behind for perhaps your next stroke of the excavation tool. And well, if you see this, you can actually look into the technology readiness levels and seeing that every step has been taken. So first the simulation results, then the validation of those results, and then trying to get it into an engineering tool. Where also people with less expertise on the discrete element modeling are also able to run simulations and to get a proper solution engineered. The next process is on the more alluvial type of deposits, where, like the nodules, where they actually lay in the seafloor, and you don't need to excavate them, but you do need to harvest them. So this development has been done for the harvesting of polymetallic nodules. The nodules lay on the seafloor, and in this case we have a collector, so the harvester, which has a relatively high speed water jet flowing above the nodules, creating an under pressure which actually sucks up the nodules in the water stream, where after it has been collected, it will be separated from the nodules. So the seafloor sediments will be separated from the nodules. The nodules will be transported to the vertical transport system, and the seafloor sediments will be returned to the seafloor. Also in this case, we started with CFD modeling. So we started with numerical experiments, simulations. Then we went to the lab, where we did a small-scale study into the behavior of those flows. Then we went to another lab in this case, where we could test it full scale, so a 1-to-1 size. And then we turned to the drawing table to incorporate all of these results into to an updated design of the harvester. This is one of the results. I'm not sure if the video can be visible to you, but I'll try it anyway. So this is a half-scale test. You can actually see nodule-like shapes on the bottom of a tank in this case, and you see the sediments and the nodules being sucked in by the harvester, and all of this under pressure is created by the high velocity water jet occurring above the nodules. So there's no contact with the seafloor in this case. The collector is hovering above the seafloor, and it's collecting the materials with that created under pressure. Now I'm going to move on to the vertical transport system. The vertical transport system is the main link between the seafloor from the seafloor mining tool and the vessel. And in case of polymetallic nodules, they need to be transported for about 5 kilometers from the seafloor to the vessel. So you have to transport them over very long distances, and that's also the time associated with the transport is a lot longer than what is custom in normal underwater mining or the dredging industry. So we have a lot longer time scales, and in those longer time scales, phenomena can play roles which don't play a role in the much shorter time distances which we currently have. So normally we transport material for, let's say, 100 meters from the seafloor to the vessel, and now it's 5 kilometers. So we try to simulate all of those phenomena, like the density waves, which can occur if you have a fluidization process, with questions like, well, those density waves, can they also occur during transport of those materials? And for that, we did again simulations. So we always start with trying to simulate the problem. In modern terms, creating a digital twin, and then we try to validate those experiments, those numerical experiments, the simulations, by doing tests. So we built a test setup in our lab in the Netherlands, where we transported materials over a height of about 10 meters. So we had 10 meters available from the floor to the rooftop of our laboratory. We did tests for I think 1.5 years in total. We created a huge amount of test data, and we used that to validate our models. Although looking at the models, which we try to run to simulate a 5-kilometer mining operation, a 5-kilometer deep mining operation, and having validation tests in the 10-meter scale, we did think we needed to do something in between. So we went to a test site in eastern Germany where we could use a abandoned mine shaft of an old silver mine. And we actually built a very similar test setup as we used in our own lab, but now over a height of 136 meters instead of 10 meters. So that's already a big step in the right direction. And we did a very similar testing campaign. So we tried to pump material, and well, the pump was actually on the not in the deepest end of the air shaft, but it was located above. We pumped the material down 136 meters to the bottom end of the shaft, and then back up 136 meters, where we fully instrumented the upgoing flow to be able to validate the models. In this case, in a larger scale than we could in our own laboratory. Not all of the equipment we need for deep sea mining needs to be developed from scratch. So, like I said, deep sea mining is, in our view, a combination of underwater mining and the oil and gas industry, and we can actually use quite a bit of technology already developed for underwater mining and oil and gas to be applicable in the deep sea mining industry. And one of the examples is the underwater vehicle. So in deep sea mining, the harvester will need to be driven around on the seafloor. So you need a subsea vehicle to do that. But subsea vehicles are already quite common in the oil and gas industry, for example, for trenching. So there are technologies already available which can be used. And with a combination of underwater mining and oil and gas, probably 70% of the technology is already available. And it's about developing the remaining 30% of the technology which is still lacking, to come to the viable technology you need for deep sea mining. And when I'm talking about technology already available, for example, riser technology. Of course, the vertical transport of material is a new phenomenon, but riser technology has been around for quite some time, and also riser dynamics. The towers you need for the deployment of a riser system, also the launch and recovery system for subsea vehicles. All of them are existing technologies which are present today and needs some minor adjustments to be suitable for deep sea mining. But of course, it is important to focus on the technologies which are not yet available and needs to be developed. And with this, I would like to conclude my presentation and available for questions if there are any.
I would like to thank you, Wiebe. Shall we continue with the next presentation? That's Henko, the Stigter, expected environmental impacts of a deep sea mining.
Yeah, if you still want to bear with me for another a bit.
Sure.
Okay, let me see. Share it. So you can hear me, you can see the screen?
Absolutely. Can you put it in presentation mode?
Oh, yeah, sure. Yeah. Oh, sorry, I don't see myself now. But who can I? Sorry. Okay, I'll just start here. So my name is Henko de Stigter. I'm working at NIOZ, the Netherlands Institute for Sea Research, located on Texel in the Netherlands and in Ierseke. My talk is titled Expected Environmental Impacts of Deep Sea Mining. And I explicitly started with the word expected because deep sea mining is an industry that's not yet existing, and there's no proven environmental impacts yet, although there's a lot that is already quite obvious that we can expect. So what is important? Yeah, what we've seen in the previous presentations is our dependence on natural resources, and then we're thinking of mineral resources and energy resources. But then the biological resources are also very important, not only because we like to have nature around us, but because we are really dependent for our existence. For food, for example, for the oxygen we breathe, which is produced by living organisms, and 50 to 80% of that by organisms living in the sea. The ocean is also a huge reservoir for taking up carbon dioxide from the atmosphere, and thus buffering our carbon emissions that we are doing for the last 150 years. So it's important to be careful when we start developing a new activity in that. And yeah, there's of course there's a balance. There's also what we hope is to see the benefits of using resources from the deep sea, the metals that we can recover there, for making this very necessary transition to more making the green transition to non-fossil energy sources. So in this, in the framework of the United Nations Law of the Sea, there's the International Seabed Authority that is that has mandate to regulate the extraction of mineral resource from the deep sea, and also to ensure that an effective protection of marine environment from serious harm. And then the question is, what is serious environmental harm? We're not speaking of destruction locally of some deep sea animals. What we're speaking of is a serious environmental harm that is impairment of regulating and provisioning functions of the ocean. For example, the primary production, production of food resources, oxygen production, nutrient cycling, and carbon dioxide sequestration, and also the loss of biodiversity. So what we do not want to see, what's actually already happening a lot, is the extinction of species. We don't want to see more species getting extinct because of our activities in the ocean. So the different types of metal-rich mineral deposits, they have been already nicely presented introduced in the previous talks, so I'll skip that. The three main types of deposits. There are different types of minerals. What's important is to see is that there are also different environmental settings, and with those also that are different ecosystems involved. So, for example, the polymetallic nodules, they're found on these very large abyssal plains, but they're found they're actually only at the surface. So extracting these nodules will affect maybe just the top 10 centimeters of the seabed, but that over hundreds of square kilometers per year for a full scale mining operation. The environment where these nodules are found, well, obviously for all deep sea deposits, there's high pressure, low temperature, low bottom current speeds. What's important is that the minerals are in a chemically stable state in their ambient environment. So the extraction will not release unstable chemical substances, in contrast to what will happen with SMS extraction. The biota of these extreme deep sea environments, they're food limited because they depend entirely on food that is settling out from the productive surface ocean layer to the seabed. And this results in very low abundances of fauna, as you can see in this typical picture of a nodule field. At first sight, there's no life here. There's low abundance, but on the other hand, there's a very high biodiversity in these areas. So if we go to polymetallic crust, they're found on seamounts. These seamounts, they have often a strong interaction with currents and with tides, and that locally can generate strong current speeds. And the interaction of topography and currents creates internal waves with strong vertical water movements and strong currents. Minerals in this environment, again, they're chemically stable. The biota, the deep sea life that is found on these seamount areas, there's often an enhanced productivity because over these seamounts, and that's causing moderate amounts of biomass and abundance of fauna and moderate biodiversity. Then if we go to these seafloor massive sulfides, they're found in a chemically relatively unstable environment with a lot of reactive chemicals around in the water. There's a variable flow of hydrothermal waters with temperatures locally up to 400 degrees Celsius. And that requires a very specialized but low diverse fauna that can tolerate these conditions. So these different environments, they will be impacted in different ways by the mining. So if we look at a typical mining operation, here's it's schematically depicted here. We see the mining vehicle collecting minerals at the seabed. Mineral slurry is transported to the surface by the vertical riser system and then processed on board of the ship and dewatered. And these different activities of the process, they generate different pressures, changes in the ambient environment, which in turn will have impacts on seabed life, on life in the ocean. So I want to just illustrate a few of them. These pressures, one of them is removal of substrate, the use of artificial light, the plumes that are generated by the collector but also by the return of water from dewatering on board and underwater noise. So we see here some pictures of polymetallic nodules in the Clarion-Clipperton zone. These are not the typical round potato-like nodules. These are found, for example, in the Belgian exploration area. But these more angular, smaller nodules are found in the German license area. The nodules or the mineral resources that are being extracted, they're often also a solid substrate. They're offering substrate to settle for deep sea fauna. They attach themselves. For example, we see here a deep sea coral attached to a nodule. And obviously, if we start removing these nodules from the seabed, we will remove the fauna with it. And also reduce the possibility for this fauna to return to these areas, unless we leave some nodules there or replace the nodules with some other artificial substrate. But also the sediment that is lying in between these nodules, it contains the basic food necessary for survival of deep sea life. So there's organic particles that settle out from the overlying water. They're concentrated in the top millimeter of this sediment in between the nodules. And there's certain fauna, for example, we see a sea cucumber here that is kind of vacuum cleaning this sediment surface and extracting the edible parts of that. And by taking up these nodules and the surrounding sediment, even if it's only a few centimeters, that will take away this essential food resource. The sediment will be left behind on the seabed, but then homogenized, and the food-rich part will be mixed with non-nutritive sediment. So here we see a picture from a recent mining test carried out by DEMA GSR in the Pacific Ocean. Oh, I should go too fast forward. We see the traces on the seabed produced by this mining vehicle. The seabed was full of nodules, densely covered, but they have been effectively taken away. So the substrate for attachment of fauna has also been taken away. And to the left of this picture, we see the sediment plume that is produced in the mining process, in the extraction process, that is still lingering on. And the object here in the center is actually an instrument that is measuring oxygen profiles to measure the respiration of the seabed after the impact. Then, if you look at the effect of the plume that is created by the collector vehicle, that has different effects on fauna. On the right, we see a picture of a deep sea sponge, which should be very white. It's a siliceous sponge, but here it's covered by a layer of mud that was settled out from this plume. And the sponge is filtering the water to collect the scarce nutrient particles from the water. And when the water is, when there's a lot of deep sea mud mixed in the water, that will start clogging this filtration system of the deep sea sponge. So it will impair the breathing and also the food collection of these suspension feeders. And again, mixing the nutritious parts of the top layer of sediment with a lot of sediment without nutritional value, that will have negative effects on this fauna. Certain types of mineral collection, and then especially in massive sulfide deposits, these deposits are chemically reactive, and the finely dispersed particles may have toxic effects on fauna when ingested. These turbid clouds in the otherwise crystal clear water, they will shield off bioluminescence. And bioluminescence, that's the light produced by deep sea organisms that they use for communication. Sorry, I'm going too fast. For attraction of prey, for deterrence of predators, that will be shielded out by turbidity. Furthermore, when these plumes, where they will settle out, locally close to the mining area, the sediment that's redeposited may bury fauna. On the left, we see a picture of buried nodules. And in the center, there's a sea anemone that apparently was not buried and it just popped out from the sediment blanket and continues its life in searching for food. But this redeposited sediment will also bury food resources for fauna that is deposit feeding, that is searching for this settled food particles on the seabed. Plumes will be generated by the collection process, but also driving around over the seabed in mid-ocean ridge settings and on seamounts where we have very steep slopes, up to several tens of degrees. Just moving around over such seabed may be enough to trigger turbidity currents. And that's what we'll see here. We are looking down at the seabed on the mid-Atlantic ridge south of the Azores. And we're looking down with a towed camera. And the operator of the camera is trying not to touch the seabed, but not always successful. And that's what we see here. A large cloud of sediment is stirred up. And then by the increased density of this water mixed with mud, it will start flowing down the slope. That's away from our field of vision here. And if we have long slopes, this may go on for until the mud cloud has reached the bottom of the slope. And then in that process, it may take up more and more sediment from the seabed and erode the substrate that is needed for deep sea fauna. Then more about plumes. Then we have the dewatering plumes that is returned from the ship. In the regulations of the ISA, it is already indicated that this plume should be released more than 1,000 meters deep, so not to interfere with phytoplankton production. But even at 1,000 meters deep, there's still a lot of life around, planktonic life. And again, this plume may impair the breathing and food collection of all kinds of pelagic organisms. The plume may contain toxic substances. Again, it may shield off bioluminescence. There's a lot of bioluminescence organisms in the free water column. And also organisms collecting food particles by spreading out a web in the water around them. When they're collecting a lot of solid particles, sediment and ore particles, that may decrease their buoyancy, so making them sink. More effects of mining, that is underwater noise. Okay, I think we know a lot about effects of noise already from seismics, for example. Deep sea mining may not create that very intense noise, more in the range of shipping, drill rig, that's so relatively moderate noise levels and low frequencies generally, but it may overlap with sound created by sea life. And well, that may interfere with communication, for example, long distance communication that whales have. It may interfere with hunting behavior. Many large sea mammals, they use sonar for detecting prey. And when that sound is masked, they may have the range of detection of prey may be decreased, obviously in the vicinity of an active mining operation. I'll skip this image. It shows the head of a sperm whale, a whale that's known to dive to more than 1 kilometer depth, and there detects giant squids, its favorite prey, by the sonar it emits. And a large part of the head of the whale is actually a sound producing an organ, and producing sound and also focusing it into a directed beam. And so a large part of the whale body is used for producing and detecting underwater sound, just to illustrate the importance of underwater sound for marine life. Then light, there will be a lot of use of artificial light in mining operations. And it's usually said that the deep sea, there's no light there. Well, that's to say there's no sunlight penetrating more than about 500 meters deep. But in the deep sea, there's a lot of light produced by all kinds of organisms. And that's what's called the bioluminescence, which I already mentioned. That's used for deterring predators, for flashing light. It's used for attraction of prey or mating partners, and also for counter-illumination, for camouflage. These organisms, they have very light-sensitive eyes, and the artificial light may have the effect that it blinds these organisms temporarily or permanently. That's what we don't know. So there's many different ways in which mining may interfere with deep sea life. Now the question is, what is the scale of this impact? We have these individual effects, and how can we scale that? What is important questions are, what is the size of the area affected by mining? And how bad is the impact? And will the environment recover? Will there be a potential for recovery? Now, the first question is relatively straightforward to answer. The mined area, that is where the mining vehicle will be active on the seabed. That's very well controlled, of course. The area impacted, especially by the sediment plume, we are well on the way to have good numerical models to produce predictions of the spreading of this plume. And combined with monitoring sensors on the seabed, we have a good grip on that part. What we do not know very well is how bad is the impact. We can expect different types of impact. We can expect that in the mined area, a lot of the organisms will be obliterated. In the impacted area, there may be less severe effects. Life may be impaired in its functions, but still surviving. Some of the effects will be only temporarily. For example, light and sound produced in a mining operation that will stop when the operation is ceased. Other effects will be more permanent. For example, the extraction, the removal of substrate. Before nodules will return, will grow back. That is a process, that's a geological process that may take millions of years. So there's long-term versus short-term effects. And there's the question, will recovery be possible? That's a lot of that is still unknown. And what I would like to explain is, why is it so difficult to know these effects on deep sea biota? We know a lot about life in shallow areas, and a lot of that is based on experiments where different life forms are exposed to pressures, for example, to toxic substances, such as sketched in this cartoon to the left. A toxic substance is administered to model organisms. And in the most brute version, what is counted is the percentage of mortality of these organisms in relation to the doses administered. So this is possible for life from shallow seas, and that's also the base of a lot of regulations. These are based on this type of experiments. But that is, that is very difficult for deep sea life. One reason is because of the vast amount of deep sea life that is still unknown. Current counts of marine species says that there are about 250,000 marine species of animals and plants that are formally described, but there's still many times more, counting up to 1 million of marine species that are still undiscovered and still undescribed. So we know only very little of species that exist in the deep sea. The vast majority of these known species, they are from shallow waters, and the number of species known from the deep sea is growing every day. So just knowing them is already a challenge. And we can't, for the species that we know from the deep sea, we can't do lab experiments to do those response experiments like we can do for shallow fauna. The reason of that is that most deep sea species can't be brought to the sea surface alive. They will, when we collect them from the deep seabed from more than 2 kilometers depth and bring them to the surface, they will suffer from heat stress and decompression effects, and making that most of them have died when they come to the surface. So the only way forward is to do in situ experiments in the deep sea. And that is shown here in the left. We see in a deep sea life, a sea cucumber contained in an incubation chamber. And there's some syringes with which substance can be administered, for example, suspended sediment. These are experiments. To do this, to carry out these experiments, you need a deep sea ROV and ROV, such as shown here on the right. And to operate a deep sea ROV, you need a large seagoing ship, research vessel, or the like. And that makes this type of experiments extremely expensive to carry out. Another way to investigate tolerance threshold, the tolerance of deep sea life, is large-scale disturbance experiments, such have been carried out already for a number of decades. And here's an example, the Discal experiment. This was carried out in the end of the 1980s, almost 30 years ago, more than 30 years ago. And in that experiment, a plow was used to simulate the effect of deep sea mining. That was the kind of tool available 30 years ago. With that plow, an area of seabed of about 1 mile across at 4 kilometers depth in the Pacific Ocean was plowed over. And then before and shortly after that plowing, samples were collected of the sediment and of living organisms. And that was repeated several years afterwards. And also quite recently, a few years ago, that was 26 years after this experiment. And the findings, even 26 years later, the furrows made by this plow are still very clearly visible. The geochemical gradients in the sediment, they are still not completely restored. And benthic fauna, some of the fauna has very well survived this disturbance experiment. Others have not returned. So the benthic fauna, after 3 decades, has only partly recovered. Well, one criticism against this experiment, well, it was not mining equipment that was used. It was just an agricultural plow to simulate the effect of mining. So to have better results, we have to wait for testing of real mining machinery. And well, we had one of these tests in this spring. Then the nodule collector of DEMA GSR was tested in the Pacific Ocean in the Clarion-Clipperton zone at about 4 kilometers depth. And on that occasion, there was a second ship available with a team of researchers, and I was one of them. And we were collecting information, observations on the effect of that mining trial. So that was done with AUV, with ROV, different types of equipment, and samples have been collected. and that provided us with information on at least the direct impacts to the seabed. But this type of monitoring has to be continued over years to come to see also the longer term impacts. And that's where I want to conclude. I think my time is well up. We've seen that exploration of deep sea mineral resources is well underway, and also the development of mining technology is moving fast forward, with equipment already being tested in the deep sea. But while that is happening, our knowledge about impact on the marine environment is very much lagging behind. And we really need monitoring of deep sea mining tests to give insight in at least the short term, the direct impacts of mining. But sustained research efforts are needed to assess also the longer term impacts. And that's the picture where I would like to stop. Now let me see if I can, oh, sorry. I'm trying to get back to I'll stop the presentation.
Yes, I would like to thank you, Henko, for your presentations. Are there any questions? Adriana needs to leave in a second. Is there any question for Adriana? No? Any questions for Henko? Okay, well then I would like to conclude the session. Thanks a lot for your patience, for your attention. I'm very sorry that we have run over time. And I wish you a very nice day.